Hi, this is lesson 4.2 on linear regression. Back in lesson 1.3 we actually mentioned the difference between a classification problem and a regression problem. A classification problem is when what you're trying to predict is a nominal value, whereas in a regression problem what you're trying to predict is a numeric value. We've seen examples of data sets with nominal and numeric attributes before, but we've never looked at the problem of regression, of trying to predict a numeric value as the output of a machine learning scheme. So that's what we're doing in this class, linear regression. We've only had nominal classes so far, so now we're going to look at numeric classes. And this is a classical statistical method dating back more than 2 centuries, I guess. And this is the kind of picture that you see. You've got a cloud of data points in 2 dimensions, and we're trying to fit a straight line to this cloud of data points, and we're looking at the best kind of straight line fit. Only in our case we might have more than 2 dimensions. There might be multiple dimensions. It's still a standard kind of problem. And let's just look at the 2-dimensional case here. You can write a straight line equation in this form with weights W0 plus W1A1 plus W2A2 and so on. Just think about this in 1 dimension where there's only one A. So forget about all the things at the end here. Just consider W0 plus W1A1. That's the equation of this line. That's the equation of a straight line where W0 and W1 are 2 constants to be determined from the data. This, of course, is going to work most naturally with numeric attributes because we're kind of multiplying these attribute values by weights. We'll worry about nominal attributes in just a minute. So we're going to calculate these weights from the training data, W0, W1 and W2. Those are what we're going to calculate from the training data. And then once we've calculated the weights, we're going to predict the value for the first training instance, A1. The notation gets really horrendous here. I know it looks pretty scary, but it's pretty simple. We're just using this linear sum with these weights that we've calculated, using the attribute values of the first test instance here, and in order to get the predicted value for that. So we're going to get predicted values for the training instances using this rather horrendous looking formula here. I know it looks pretty scary, but it's actually not so scary. These W's are just numbers that we've calculated from the training data. And then these things here are the attribute values of the first training instance, A1. That's the 1 at the top here, means it's the first training instance. This kind of 1, 2, 3 means it's the first, second and third attribute. And we can write this in this neat little sum form here, which looks a little bit better. Notice, by the way, that we're defining A0, the 0th attribute value, to be 1. That just makes this formula kind of work. Anyway, for the first training instance, it might be this one here, that gives us this number x, the predicted value for the first training instance at this particular value of A1. And then what we're doing then, we're choosing the weights to minimize the squared error on the training data. So this is the actual x value for this ith training instance. This is the predicted value for the ith training instance. So we're going to take the difference between the actual and the predicted value, square them up and add them all together. And that's what we're trying to minimize. So where we get these weights from is we get the weights by minimizing this sum of squared errors. That's a mathematical job that we don't need to worry about the mechanics of doing that. It's a standard matrix problem. It works fine if there are more instances than attributes. You couldn't expect this to work if you had a huge number of attributes and not very many instances. But providing there are more instances than attributes, and usually there are, of course, then it's going to work okay. If we did have nominal values, well, if we just had a 2-valued, a binary value, 0 and 1, we could just convert it to 0 and 1 and use those numbers. If we had multi-valued nominal attributes, well, you'll have a look at that in the activity at the end of this lesson. Okay, let's do it then. We're going to open a regression data set, cpu.arf. Now this is a regular kind of data set. It's got numeric attributes, and the most important thing here is it's got a numeric class. We're trying to predict a numeric value. And we can just go and run linear regression. It's in the functions category, functions linear regression, and we just run it, and this is the output. We've got the model here. That's the class is being predicted as a linear sum. These are the weights I was talking about. So it's this weight times this attribute value plus this weight times this attribute value, and so on, minus, and this is the W naught, the kind of the weight that's just a constant kind of weight, not modified by an attribute value. So this is a formula for computing the class. And when you use that formula, you can look at the success of it in terms of the training data. The correlation coefficient, which is a standard statistical measure, is 0.9. That's pretty good. And then there's various other error figures here that are printed. On the slide you can see the interpretation of these error figures. It's really hard to know which one to use. They all tend to produce the same sort of picture, but I guess the exact one you should use depends on the application. There's a mean absolute error, the root mean squared error, which is kind of the standard metric to use, I guess. Okay, that's linear regression. Now I'm actually going to look at non-linear regression here. A model tree is a tree where each leaf has got one of these linear regression models. So we kind of create a tree like this, and then at each leaf we have a linear model which has got those coefficients. So it's kind of like a patchwork of linear models, and these kind of, this set of, in this case, 1, 2, 3, 4, 5, 6 linear patches approximate a continuous function. So there's a method under trees with a rather mysterious name of M5P, and if we just run that, that produces a model tree. Maybe I should just visualize the tree here, and now I can see the model tree. It's similar to the one on the screen, on the slide. And you can see that each of these, in this case 5 leaves, has got a linear model LM1, LM2, LM3. And if we look back here, the linear models are defined like this. LM1 has got a formula, this linear formula for LM1, this linear formula from LM2, and so on. So we chose trees M5P, we ran it and we looked at the output. We could compare the performance of these performance figures, 92, 93% correlation, mean absolute error of 30, and so on. We could compare those with the ones for the regular linear regression, which has got a slightly lower correlation and a slightly higher absolute error. In fact, I think all of these error figures are slightly higher. That's something we'll be asking you to do in the activity associated with this lesson. So linear regression is a well-founded, venerable mathematical technique, but practical problems often require nonlinear solutions. So M5P, the M5P method builds trees of regression models with linear models at each leaf of the tree. You can read about this in the course text in section 4.6. And off you go now and do the activity associated with this lesson. We'll see you soon. Bye.